Hello students. Today we are going to study a very important and equally interesting chapter of grade 10 physics, electricity. We would do a walkthrough of the chapter, and in between I would keep telling you the important points, formulas and questions that come from their respective parts of the chapter. So stay with me, pay good attention, and this so-called difficult chapter of electricity would become one of your favorite chapters. The way we would cover the chapter today would be more interesting than the traditional way of studying, I promise you that. So let's begin. Electricity has an important place in modern society. It is a controllable and convenient form of energy for a variety of uses in homes, schools, hospitals, industries, and so on. These are the main topics that we would be talking about in this chapter. But first, we need to understand what constitutes electricity. How does it flow in an electric circuit? What are the factors that control or regulate the current through an electric circuit? We shall also discuss the heating effect of electric current and its applications. Let's begin with electric current and circuit. We are familiar with air current and water current. We know that flowing water constitute water currents in rivers. Similarly, if the electric charge flows through a conductor like a metallic wire, we say that there is an electric current in the conductor. This here is important to understand, so I would reiterate it. The flow of electric charge through a conductor such as a metallic wire constitutes the electric current in it. In a torch, we know that the cells or battery, when placed in proper order, provide flow of charges or an electric current through the torch bulb to glow. We have also seen that the torch gives light only when its switch is on. What does a switch do? A switch makes a conducting link between the cell and the bulb. Now, this continuous and closed path of an electric current is called an electric circuit. Now, if the circuit is broken anywhere or the switch is turned off, the current stops flowing and the bulb does not glow. Now, if you have understood the concept of current, circuit and switch, please write yes to 1 in comment section below, and then let's move further. Now, how do we express electric current? Electric current is expressed by the amount of charge flowing through a particular area in a unit time. In other words, it is the rate of flow of electric charges. In circuits using metallic wires, electrons constitute the flow of charges. However, electrons were not known at the time when the phenomena of electricity was first observed. So, electric current was considered to be the flow of positive charges, and the direction of flow of positive charges was taken to be the direction of electric current. Conventionally, in an electric circuit, the direction of electric current is taken as the opposite to the direction of the flow of electrons, which we know are negative charges. If a net charge, say Q, flows across any cross-section of a conductor in time, say t, then the current I through the cross-section is given by Q by t. That means current is net charge per unit time. Now let's talk about the charge first. The SI unit of electric charge is coulomb, which is equivalent to the charge contained in nearly 6 into 10 raised to the power 18 electrons. Now, do you remember how much charge does an electron possess? Well, an electron possesses a negative charge of 1.6 into 10 raised to the power minus 19 coulomb. Now moving back to current. The electric current is expressed by a unit called ampere. It is named after the French scientist Henri-Marie Ampere. 1 ampere is constituted by the flow of 1 coulomb of charge per second. That is, 1A is 1C by 1S. This question can come in the form of define the unit of current, and we would say that 1 ampere measures the flow of electric charge across a surface at the rate of 1 coulomb per second. Small quantities of current are expressed in milliampere, which is 10 raised to the power minus 3 amperes, or in microampere, which is 10 raised to the power minus 6 ampere. An instrument called ammeter measures electric current in a circuit. Please note that it is always connected in series in a circuit through which the current is to be measured. Now, why is that? There are two main reasons for doing that. First, since current remains same in series connection, ammeter would give the correct reading of the current passing through the circuit. And secondly, since the resistance of an ammeter is very small, hence it doesn't affect the current to be measured when we connect it in series. Here is the schematic diagram of a typical electric circuit comprising a cell, an electric bulb, an ammeter, and a plug key. Note that the electric current flows in the circuit from the positive terminal of the cell to the negative terminal of the cell through the bulb and ammeter, of course. So now, if I ask you, what does an electric circuit mean? The answer would be, it is an electric current transmission path that consists of a device that provides energy to the charged particles that make up the current, such as a battery, as well as the devices that use the current, like an electric bulb and the connecting wires or transmission lines. Pretty interesting till now, right? Let's see an example now. A current of 0.5 amperes is drawn by a filament of an electric bulb for 10 minutes. Find the amount of electric charge that flows through the circuit. We are given current as 0.5 amperes. That means I is 0.5 amperes. T is 10 minutes, which is 600 seconds. We have Q equal to IT. So, current is 0.5, time is 600, charge would be 0.5 into 600, which gives us 300 coulomb. Pretty easy, right? Now let's go through some more questions. Actually, let's solve one more question. Let's calculate the number of electrons constituting 1 coulomb of charge. We are given that charge is 1 coulomb. We have to find the number of electrons constituting 1 coulomb of charge. Now, total charge would be equal to the number of electrons into the charge of 1 electron, right? Now, charge of 1 electron, as we just discussed, is 1.6 into 10 raised to the power minus 19. Hence, total charge, that is 1, is equal to n into 1.6 into 10 raised to the power minus 19, which gives us n as 6.25 into 10 raised to the power 18. Hence, the number of electrons constituting 1 coulomb of charge is 6.25 into 10 raised to the power 18. That was simple as well as interesting, isn't it? Now, if I ask you, have you ever wondered how does a metal conduct electricity? For that, let's see the flow of charges inside a wire. You would think that a low energy electron would have great difficulty passing through a solid conductor. Inside the solid, the atoms are packed together with very little spacing between them. But it turns out that the electrons are able to travel through a perfect solid crystal smoothly and easily, almost as if they were in a vacuum. The motion of electrons in a conductor, however, is very different from that of charges in empty space. When a steady current flows through a conductor, the electrons in it move with a certain average drift speed. One can calculate this drift speed of electrons for a typical copper wire carrying a small current, and it is found to be actually very small, of the order 1 millimeter per second. Now, if the drift speed is that small, how is it that an electric bulb lights up as soon as we turn the switch on? It cannot be that a current starts only when an electron from one terminal of the electric supply physically reaches the other terminal through the bulb, because the physical drift of the electrons in the conducting wires is a very slow process. The exact mechanism of the current flow, which takes place with the speed close to the speed of light, is fascinating, but it is beyond the scope here. For now, let's just understand that it is not that an electron starts from the battery and reaches the bulb, but that the battery sets up an electric field that leads to the motion of all the free electrons in the wire from the positive end of the battery towards the negative end. If you got it, let us know in the comment section below. If you're liking the video, don't forget to hit the like button for us to know. Our next topic is electric potential and potential difference. Do you wonder what makes the electric charge to flow? Charges do not flow in a copper wire by themselves. Let us consider the analogy of flow of water. Water in a perfectly horizontal tube does not flow. If one end of the tube is connected to a tank of water kept at a higher level such that there is a pressure difference between the two ends of the tube, water flows out the other end of the tube. For flow of charges in a conducting metallic wire, the gravity, of course, has no role to play. The electrons move only if there is a difference of electric pressure called the potential difference along the conductor. This difference of potential may be produced by a battery consisting of one or more electric cells. The chemical action within a cell generates the potential difference across the terminals of the cell, even when no current is drawn from it. When the cell is connected to a conducting circuit element, the potential difference sets the charges in motion in the conductor and produces an electric current. In order to maintain the current in a given electric circuit, the cell has to expand its chemical energy stored in it. We define the electric potential difference between 2 points in an electric circuit carrying some current as the work done to move a unit charge from one point to the other. Potential difference between 2 points is work done per unit charge. The SI unit of electric potential difference is volt, named after Alessandro Volta, an Italian physicist. 1 volt is the potential difference between 2 points in a current carrying conductor when 1 joule of work is done to move a charge of 1 coulomb from one point to the other. I repeat, the potential difference between 2 points in a conductor when 1 joule of work is done to move a charge of 1 coulomb from one point to the other. Therefore, 1 volt is 1 joule by 1 coulomb. The potential difference is measured by means of an instrument called the voltmeter. The voltmeter is always connected in parallel across the points between which the potential difference is to be measured. Let's solve an example now. How much work is done in moving a charge of 2 coulomb across 2 points having a potential difference of 12 volt? The amount of charge that flows between the 2 points at potential difference is 2 coulomb. Thus, the amount of work done in moving the charge would be V times Q, which is 12 times 2, which is 24 joules. Let's see one more. how much energy is given to each coulomb of charge passing through a 6-volt battery. Now, since W is V into Q, 6 joules of energy is given to each coulomb of charge passing through a 6-volt battery. If you're liking the video, hit the like button for us and let us know too. Next is circuit diagram. We know that an electric circuit comprises of a cell, a plug key, electrical components and connecting wires. It is often convenient to draw a schematic diagram in which different components of the circuit are represented by the symbols conveniently used. Conventional symbols used to represent some of the most commonly used electrical components are given here. You might want to take a screenshot of this. Let's see the Ohm's law now. In 1827, a German physicist, Simon Ohm, found out the relationship between the current I flowing in a metallic wire and the potential difference across its terminals. The potential difference V across the ends of a given metallic wire in an electric circuit is directly proportional to the current flowing through it, provided its temperature remains the same. That means it varies with the change in temperature. Now, this is called Ohm's law. In other words, V is directly proportional to I. That means V upon I is a constant, which is equal to R. Hence, V is I times R. R is a constant for the given metallic wire at a given temperature and is called its resistance. It is the property of a conductor to resist the flow of charges. Its SI unit is ohm, represented by the Greek letter omega. According to Ohm's law, R is V upon I. If the potential difference across the two ends of a conductor is 1 volt and the current through it is 1 amperes, then the resistance R of the conductor is 1 ohm. That is, 1 ohm is 1 volt by 1 ampere. It is obvious that the current through a resistor is inversely proportional to its resistance. If the resistance is doubled, the current gets halved. In many practical cases, it is necessary to increase or decrease the current in an electric circuit. A component used to regulate current without changing the voltage source is called variable resistance. In an electric circuit, a device called rheostat is often used to change the resistance in the circuit. Do you know? The current is different for different components. Now the question is, why do they differ? Well, that is because certain components offer an easy path for the flow of electric current while the others resist the flow. We know that motion of electrons in an electric circuit constitutes an electric current. The electrons, however, are not completely free to move within a conductor. They are restrained by the attraction of the atoms among which they move. Thus, motion of electrons through a conductor is retarded by its resistance. A component of a given size that offers a low resistance is a good conductor. On the other hand, a conductor having some appreciable resistance is called a resistor. Now, a component of identical size that offers a higher resistance is a poor conductor. And an insulator of the same size offers even higher resistance. Now let's see the factors on which the resistance of a conductor depends. In an electric circuit, it is observed that the ammeter reading decreases to 1/2 when the length of the wire is doubled. The ammeter reading is increased when a thicker wire of the same material and of the same length is used in the circuit. A change in ammeter reading is observed when a wire of different material of the same length and the same area of cross section is used. On applying Ohm's law, R is V upon I. Thus, we observe that the resistance of the conductor depends on its length, on its area of cross section, and on the nature of its material. Precise measurements have shown that resistance of a uniform metallic conductor is directly proportional to its length and inversely proportional to the area of cross section. This is very important here, you might want to note it. That is, R is directly proportional to L, it is inversely proportional to A. So, R is directly proportional to L by A. R is equal to rho into L by A, where rho is a constant of proportionality and is called the electrical resistivity of the material of the conductor. It is a characteristic property of the material. The SI unit of resistivity is ohm meter. The metals and alloys have very low resistivity in the range of 10 raised to the power minus 8 ohm meter to 10 raised to the power minus 6 ohm meter. They are good conductors of electricity. Insulators like rubber and glass have resistivity of the order of 10 raised to the power 12 to 10 raised to the power 17 ohm meter. Both the resistance and resistivity of a material vary with temperature. The resistivity of an alloy is generally higher than that of its constituent metals. Alloys do not oxidize or burn readily at high temperatures. This is the reason why they are commonly used in electrical heating devices like electric iron, toasters, etc. Tungsten is used almost exclusively for filaments of electric bulbs, whereas copper and aluminium are generally used for electrical transmission lines. Hope you're liking the video. In that case, do give us a thumbs up and let us know too. Moving on. Let us see a few examples now. How much current will an electric bulb draw from a 220 volt source if the resistance of the bulb filament is 1200 ohms? And we are given V is 220 volt, R is 1200, and we know that I is V upon R. Hence, current is 220 upon 1200. That is 0.18 amperes. Moving on to the next one. How much current will an electric heater coil draw from a 220 volt source if the resistance of the heater coil is 100? We are given V is 220, R is 100. Now we know that current is V upon R, which gives us 2.2 amperes. Now you got to note the difference of current drawn by an electric bulb and an electric heater from the same 220 volt source. Let's see one more example. The potential difference between the terminals of an electric heater is 60 volt when it draws a current of 4 amperes from the source. What current will the heater draw if the potential difference is increased to 120 volts? We are given that potential difference is 60. According to Ohm's law, R is 60 upon 4, which is 15. When the potential difference is increased to 120, the current would be V upon R, which is 120 upon 15. That is 8 amperes. Thus, the current through the heater becomes 8 amperes. Resistance of a metal wire of length 1 meter is 26 at 20 degrees Celsius. If the diameter of the wire is 0.3 millimeter, what will be the resistivity of the metal at that temperature? We are given the resistance as 26 ohms. The diameter is 0.3 millimeter. Therefore, the resistivity of the given metallic wire is R into A upon L. Now, area would be pi r square, which means pi into d square by 4. Substitution of the values in this gives rho as 1.84 into 10 raised to the power minus 6 ohm meter. The resistivity of the metal at 20 degrees Celsius is 1.84 into 10 raised to the minus 6 ohm meter. Now, if we were to predict the material of the wire, from this table we see that this is the resistivity of manganese. Let's see one more. A wire of given material having length L and area of cross section A has a resistance of 4 ohms. What would be the resistance of another wire of the same material having length L by 2 and the area of cross section 2A? Now, for the first wire, R1 is 4 ohms and R2 would be resistivity into L by 2 into 2, L by 2 upon 2 amperes. So, it will be rho times L by 2 divided by 2A. So, it will be 1 by 4 times R1, which is 1 ohm. Let's do a quick recap of some of the topics covered so far. On what factors does the resistance of a conductor depend? There are 4 factors that influence the resistance in a conductor. Thickness, that is the cross-sectional area of the wire, length, and temperature. The 4th factor is the conductivity of the material that is used. Some metals like copper and silver are just more electrically conductive than others like iron and aluminum. Will current flow more easily through a thick wire or a thin wire of the same material when connected to the same source, and why? The current will flow more easily through a thick wire than through a thin wire of the same material when connected to the same source. This is due to the fact that resistance of a wire is inversely proportional to the square of its diameter. The resistance of an electrical component remains constant while the potential difference across the two ends of the component decreases to half of its former value. What change will occur in the current through it? According to Ohm's law, V is IR. So I is V upon R. New potential difference would be V upon 2. So new current would be half of the original current. Thus, the amount of current flowing through the electrical component would be reduced to half its original value. Why are coils of electric toaster and electric irons made up of an alloy rather than a pure metal? An electric toaster and iron coils are made of an alloy rather than a pure metal because an alloy has a higher resistance than a pure metal. Also, the alloys do not melt easily at high temperatures. Which among iron and mercury is a better conductor? As the resistivity of iron is less than that of mercury, iron is a better conductor of electricity. Hope you're liking the video. Do subscribe to the channel if you haven't already. Resistance of a system of resistors. In various electrical gadgets, we often use resistors in various combinations. We now therefore intend to see how Ohm's law can be applied to combinations of resistors. There are 2 methods of joining the resistors together. Here is an electric circuit in which 3 resistors having resistances R1, R2 and R3 respectively are joined end to end. Here, the resistors are said to be connected in series. Shown here is a combination of resistors in which 3 resistors are connected together between points A and B. Here, the resistors are said to be connected in parallel. Let's first see the resistors in series. What happens to the value of current when a number of resistors are connected in series in a circuit? What would be their equivalent resistance? These concepts are very important, so let us try to understand these. Firstly, in a series combination of resistors, the current is the same in every part of the circuit, the same current through each resistor. On the other hand, the total potential difference across a combination of resistors in series is equal to the sum of potential difference across the individual resistors. That is, V is equal to V1 plus V2 plus V3. Let I be the current through the circuit. The current through each resistor is also I. It is possible to replace the three resistors joined in series by an equivalent single resistor of resistance R, such that the potential difference V across it and the current I through the circuit remains the same. Applying the Ohm's law to the entire circuit, we have V is equal to IR. On applying Ohm's law to the three resistors separately, we further have V1 equal to IR1, V2 is equal to IR2 and V3 equal to IR3. Now from these equations we have IR equal to IR1 plus IR2 plus IR3, or we can say R of series, that is RS, is equal to R1 plus R2 plus R3. We can conclude that when several resistors are joined in series, the resistance of the combination Rs equals the sum of their individual resistances, which are R1, R2 and R3, and is thus greater than any individual resistance. Let's solve an example now. An electric lamp whose resistance is 20 ohms and a conductor of 4 ohm resistance are connected to a 6 volt battery. Calculate the total resistance of the circuit, the current through the circuit, the potential difference across the electric lamp and conductor. The resistance of the electric lamp is 20 ohms. Let's say it is R1. The resistance of the conductor connected in series is R2, which is 4 ohms. Then the total resistance in the circuit would be R1 plus R2, which is 20 plus 4, that is 24 ohms. The total potential difference across the two terminals of the battery given is 6 volts. Now by Ohm's law, the current through the circuit is given by I equal to V by R. So it will be 6 by 24, that is 1 by 4 amperes. Applying Ohm's law to the electric lamp and conductor separately, we get potential difference across the electric lamp V1 equal to 20 ohms into 1 by 4, that is 0.25 amperes, which is 5 volts. That across the conductor would be V2, which is equal to 4 into 0.25, which is 1 volt. Suppose that we like to replace the series combination of electric lamp and conductor by a single and equivalent resistor. Its resistance must be such that a potential difference of 6 volt across the battery terminals will cause a current of 0.25 amperes in the circuit. The resistance R of the equivalent resistor would be R is equal to V by I, which is 6 by 0.25, which is 24 ohms. This is the total resistance of the series circuit. It is equal to the sum of the two resistances. Now, if we are to draw a schematic diagram of a circuit consisting of a battery of 3 cells of 2 volt each, a 5 ohm resistor, an 8 ohm resistor and a 12 ohm resistor and a plug key, all connected in series, it would look like. Here you can see all the given components connected in series. Now, if we have to redraw the circuit of the previous question, putting in an ammeter to measure the current through the resistors and a voltmeter to measure the potential difference across the 12 ohm resistor, what would be the readings in the ammeter and the voltmeter? Here resistance R is 5 plus 8 plus 12, which is 25 ohms. I is equal to V by R, which is 0.24 amperes. V is equal to IR, which is 2.88 volt. Hence, reading in ammeter would be 0.24 amperes, while reading in voltmeter would be 2.88 volts. Next is resistors in parallel combination. Now, let us consider the arrangement of three resistors joined in parallel with a combination of cells or a battery. It is observed that the total current I is equal to the sum of the separate currents through each branch of the combination. I is equal to I1 plus I2 plus I3. Let Rp be the equivalent resistance of the parallel combination of resistors. By applying Ohm's law to the parallel combination of resistors, we have I is equal to V upon Rp. On applying Ohm's law to each resistor, we have I1 equal to V upon R1, I2 equal to V upon R2, and I3 equal to V upon R3. That means V upon Rp is equal to V upon R1 plus V upon R2 plus V upon R3. Or we can say that 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Thus, we may conclude that the reciprocal of the equivalent resistance of a group of resistances joined in parallel is equal to the sum of the reciprocals of the individual resistances. You can note it. Now let's see an example. In the circuit diagram given here, suppose the resistors R1, R2 and R3 have the values 5 ohm, 10 ohm, 30 ohm respectively, which have been connected to a battery of 12 volt. Let's calculate the current through each resistor, the total current in the circuit and the total circuit resistance. Now R1 is 5 ohms, R2 is 10 ohms and R3 is 30 ohms. Potential difference across the battery is 12 volt. This is also the potential difference across each of the individual resistor. Therefore, to calculate the current in the resistors, we use Ohm's law. The current I1 through R1 is equal to V upon R1. So, I1 is equal to 12 upon 5, which is 2.4 amperes. The current I2 through R2 is V upon R2. So, I2 is equal to 12 upon 10, which is 1.2 amperes. The current R3 would be V upon R3. So it will be 12 upon 30, which is 0.4 amperes. The total current in the circuit would be I1 plus I2 plus R3. So 2.4 plus 1.2 plus 0.4, which is 4 amperes. The total resistance Rp is given by 1 by Rp equal to 1 by 5 plus 1 by 10 plus 1 by 30. So Rp is 3 ohms. Let's take one more example. If, as shown here, R1 is equal to 10 ohms, R2 is 40, R3 is 30, R4 is 20 and R5 is 60 ohms, and a 12 volt battery is connected to the arrangement, calculate the total resistance in the circuit and the total current flowing in the circuit. Suppose we replace the parallel resistors R1 and R2 by an equivalent resistor of resistance R dash. Similarly, we replace the parallel resistors R3, R4 and R5 by an equivalent single resistor of resistance R double dash. So 1 by R dash would be 1 by 10 plus 1 by 40. So R dash is 8 ohms. Similarly, 1 by R double dash would be 1 by 30 plus 1 by 20 plus 1 by 60. So R double dash would be 10 ohms. Thus, the total resistance would be R dash plus R double dash, which is 18 ohms. Let's calculate the current using the Ohm's law. We get I is equal to V by R. So 12 upon 18, which is 0.67 amperes. We have seen that in a series circuit, the current is constant throughout the electric circuit. Thus, it is obviously impracticable to connect an electric bulb and an electric heater in series because they need currents of widely different values to operate properly. Another major disadvantage of a series circuit is that when one component feels the circuit is broken and none of the components work. If you have used fairy lights to decorate buildings on festivals or marriage celebrations, etc., you might have seen the electrician spending lot of time in trouble locating and replacing the dead bulb. Each has to be tested to find which has fused or gone. On the other hand, a parallel circuit divides the current through the electrical gadgets. The total resistance in a parallel circuit is decreased. This is particularly helpful when each gadget has different resistance and requires different current to operate properly. Let's see a few examples now. Judge the equivalent resistance when the following are connected in parallel. A. 1 ohm and 10 raised to the power 6 ohm. B. 1 ohm, 10 raised to the power 3 and 10 raised to the power 6 ohm. In case of 1 ohm and 10 raised to the power 6 ohm, the resistance would be given by 1 by R equal to 1 by 1 plus 1 by 10 raised to the power 6, which gives us R as 1 ohms. Hence, the equivalent resistance is 1 ohms. In the second case, 1 by R is equal to 1 by 1 plus 1 by 10 raised to the power 3 plus 1 by 10 raised to the power 6, which gives us R as 0.999 ohms. Next, an electric lamp of 100 ohms, a toaster of resistance 50 ohms, and a water filter of resistance 500 ohms are connected in parallel to a 220 volt source. What is the resistance of an electric iron connected to the same source that takes as much current as all three appliances, and what is the current through it? Now, total resistance would be calculated as 1 by R equal to 1 by R1 plus 1 by R2 plus 1 by R3. Thus, 1 by 100 plus 1 by 50 plus 1 by 500, which gives us R as 500 by 16 ohms. Now, to find the electric current through the electric iron, according to the Ohm's law, V is equal to IR. Hence, R would be V upon I. Substituting the given values, we get I as 7.04 amperes. Therefore, the resistance is 31.25 ohms and the current is 7.04 amperes. Next question is, what are the advantages of connecting electrical devices in parallel with the battery instead of connecting them in series? Well, the advantages are the voltage across each electrical device is the same and the device can take current as per its resistance. Separate on-off switches can be applied across each device. Then, the total resistance in parallel circuits decreases. Therefore, a greater current may be drawn from the cell. Also, if one electrical device is damaged, it will not affect the other devices connected in parallel. Hence, the other devices continue to work properly. Moving on to the next question. How can three resistors of resistances 2, 3 and 6 ohm be connected to give a total resistance of 4 ohms and then also connected to give a resistance of 1 ohm? So, in the first case, to get a total resistance of 4 ohms, first connect the two resistors of 3 and 6 ohm in parallel to get a total resistance of 2 ohms, which is less than the lowest individual resistance, and then connect it in series with the 2 ohms resistor. We would get 4 ohms as the equivalent resistance. In the next part, to get a total of 1 ohm equivalent resistance, when R1, R2 and R3 are connected in parallel, we get 1 by R equal to 1 by 2 plus 1 by 3 plus 1 by 6, giving us a total resistance of 1 ohm. So, all three would be connected in parallel. Next is, what is the highest and the lowest total resistance that can be secured by combinations of 4 coils of resistances 4, 8, 12 and 24 ohms? The highest will be when connected in series, so it will be 4 plus 12 plus 8 plus 24, that is 48 ohms. And the lowest would be when connected in parallel. That will be 1 by 4 plus 1 by 8 plus 1 by 24 plus 1 by 12, thus giving us R as 2 ohms. Hey guys, don't forget to hit the like button, subscribe to the channel and press the bell icon for future updates. Next is the heating effect of electric current. We know that a battery or a cell is a source of electrical energy. The chemical reaction within the cell generates the potential difference between its two terminals that sets the electrons in motion to flow the current through a resistor or a system of resistors connected to the battery. We have also seen that to maintain the current, the source has to keep expending its energy. Where does this energy go? A part of the source energy is used in maintaining the current, may be consumed into useful work like in rotating the blades of an electric fan. The rest of the source energy may be expended to generate heat, to raise the temperature of the gadget. We often observe this in our everyday life. For example, an electric fan becomes warm if used continuously for longer time. On the other hand, if the electric circuit is purely resistive, that is, a configuration of resistors only connected to a battery, the source energy continually gets dissipated entirely in the form of heat. This is known as the heating effect of electric current. This effect is utilized in devices such as electric heater, electric iron, etc. Consider a current I flowing through a resistor of resistance R. Let the potential difference across it be V. Let T be the time during which a charge Q flows across. The work done in moving the charge Q through a potential difference V is VQ. Therefore, the source must supply energy equal to VQ in time T. Hence, the power input to the circuit by the source is V into Q by T, which is V into I, or the energy supplied to the circuit by the source in time T is P into T, that is V into I into T. Now, what happens to this energy expended by the source? This energy gets dissipated in the resistor as heat. Thus, for a steady current I, the amount of heat H produced in time T is H equal to V into I into T. Applying Ohm's law, we get H equal to I square RT. This is known as Joule's law of heating. The law implies that heat produced in a resistor is directly proportional to the square of the current for a given resistance. It is directly proportional to the resistance for a given current and directly proportional to the time for which the current flows through the resistor. In practical situations, when an electric appliance is connected to a known voltage source, equation H equal to I square RT is used after calculating the current through it, using the relation I equal to V upon R. Now let's see one example. An electric iron consumes energy at a rate of 840 watt when heating is at the maximum rate and 360 watt when the heating is at the minimum. The voltage is 220 volt. What are the current and the resistance in each case? When heating at max rate, power is 840 watts, voltage is 220 volt, and we know that P is equal to VI. 840 would be equal to 220 into I, which gives us I as 4 amperes. R is V upon I, so it will be 220 upon 4, which is 55 ohms. So current is 4 amperes and resistance is 55 ohms. When heating at minimum rate, power is 360 watts, voltage is 220 volt again, and we know that P is equal to VI. Substituting, we get I equal to 360 upon 220, that is 1.636 amperes. R is V upon I. Substituting the values, we get R equal to 134.45 ohms. So current is 1.636 amperes and resistance is 134.45 ohms. Pretty simple, right? One more. 100 joules of heat is produced each second in a 4 ohm resistance. Find the potential difference across the resistor. H is 100 joules, R is 4 ohms, T is 1 second. We have to find the potential difference. We have the current through the resistor as I equal to square root of H upon RT, which is 5 amperes on substituting the given values. Thus, the potential difference across the resistor is given by V equal to IR, which is equal to 5 into 4, that is 20 volts. Do you know why does the cord of an electric heater not glow while the heating element does? Well, the heat produced by the electric current is directly proportional to the resistance, as we know. Now, the heater element has very high resistance, so a lot of heat is produced in the heater element, due to which it becomes very hot and it glows. On the other hand, the cord of an electric heater has very low resistance, due to which very little heat is produced in it, and so the cord becomes slightly warm but doesn't glow. Let's see the next question now. Compute the heat generated while transferring 96,000 coulomb of charge in 1 hour through a potential difference of 50 volts. Given charge is 96,000 coulomb, time is 1 hour, which is 3600 seconds. Now potential difference is 50 volts. We know the formula current is equal to Q upon T. By substituting the values, we get current equal to 80 upon 3 amperes. Now to find the heat generated, H is equal to V into I into T. Substituting the given values, we get H is equal to 50 into 80 upon 3 into 3600, which is 4.8 into 10 raised to the power 6 joules. Next, an electric iron of resistance 20 ohms takes a current of 5 amperes. Calculate the heat developed in 30 seconds. As per Joule's law of heating, H is equal to I square RT. Substituting the values, we get H is equal to 5 into 5 into 20 into 30, that is 15,000 joules. Now let's see the practical applications of heating effect of electric current. The generation of heat in a conductor is an inevitable consequence of electric current. In many cases, it is undesirable as it converts useful electrical energy into heat. In electric circuits, the unavoidable heating can increase the temperature of the components and alter their properties. However, heating effect of electric current has many useful applications too. The electric laundry iron that we use, electric toaster, electric oven, kettle, and heater are some of the familiar devices based on Joule's heating. The electric heating is also used to produce light, as in an electric bulb. Here, the filament must retain as much of the heat generated as is possible, so that it gets very hot and emits light. It must not, however, melt at such high temperature. A strong metal with high melting point, such as tungsten, which has a melting point of 3380 degrees Celsius, is used for making bulb filaments. The filament should be thermally isolated as much as possible, using insulating support, etc. The bulbs are usually filled with chemically inactive nitrogen and argon gases to prolong the life of the filament. Most of the power consumed by the filament appears as heat, but a small part of it is in the form of light radiated. Another common application of Joule's heating is the fuse used in electric circuits. It protects circuits and appliances by stopping the flow of any unduly high electric current. The fuse is placed in series with a device. It consists of a piece of wire made of a metal or an alloy of appropriate melting point. For example, aluminium, copper, iron, lead, etc. Note that the melting point of lead here is 327.5 degrees Celsius. Let's see how does a fuse work. If a current larger than the specified value flows through the circuit, the temperature of the fuse wire increases. This melts the fuse wire and breaks the circuit. The fuse wire is usually encased in a cartridge of porcelain or similar material with metal ends. The fuses used for domestic purposes are rated as 1A, 2A, 3A, 5A, 10A, etc. For an electric iron which consumes 1 kilowatt electric power when operated at 220 volt, a current of 1000 by 220 amperes, that is 4.4 ampere, will flow in the circuit. In this case, a 5 ampere fuse must be used. If you're liking the video, do hit the like button and subscribe to the channel. Also press the bell icon to get the future updates. The last topic of this interesting chapter is electric power. We know that the rate of doing work is power. This is also the rate of consumption of energy. H equal to I square RT gives the rate at which electric energy is dissipated or consumed in an electric circuit. This is also termed as electric power. The power P is given by P equal to VI, which means P equal to I square R or V square by R. The SI unit of electric power is watt. It is the power consumed by a device that carries 1 ampere of current when operated at a potential difference of 1 volt. Thus, 1 watt equal to 1 volt into 1 ampere equal to 1 VA. The unit watt is very small. Therefore, in actual practice, we use a much larger unit called kilowatt. It is equal to 1000 watts. Since electrical energy is the product of power and time, the unit of electric energy is therefore watt-hour. 1 watt-hour is the energy consumed when 1 watt of power is used for 1 hour. The commercial unit of electric energy is kilowatt-hour, commonly known as unit. Kilowatt-hour equal to 1000 watt into 3600 seconds, which is equal to 3.6 into 10 raised to the power 6 watt second, which is called as joule. Many people think that electrons are consumed in an electric circuit. This is wrong. We pay the electricity board or electric company to move electrons through the electric gadgets like electric bulb, fan, and engines. We pay for the energy that we use. Now let's see an example. An electric bulb is connected to a 220 volt generator. The current is 0.5 amperes. What is the power of the bulb? P is given by V into I. So it will be 220 into 0.5, that is 110 watts. An electric refrigerator rated 400 watt operates 8 hours per day. What is the cost of the energy to operate it for 30 days at Rs 3 per kilowatt hour? The total energy consumed by the refrigerator in 30 days would be 400 into 8 hours per day into 30 days, which is 96 kilowatt hour. Thus, the cost of energy to operate the refrigerator for 30 days is 96 into 3, that is rupees 288. Moving on. Now, if I ask you, what determines the rate at which energy is delivered by a current? We know that electric power is the rate at which electrical energy is transferred by an electric current per unit of time. Hence, electric power determines the rate at which energy is delivered by a current. Now let's see one more example. An electric motor takes 5 amperes from a 220 volt line. Determine the power of the motor and the energy consumed in 2 hours. P equal to VI, which is equal to 220 into 5, hence 1100 watt. Now energy is P into T, so it will be 1100 into 2 into 60 into 60, that is 7.9 into 10 raised to the power 6 joule. Yay, we just completed the chapter. If you have any doubts, let us know in the comment section below and we would try to help you with that. Good luck. Don't forget to send us some love. We too worked very hard to make this chapter interesting and easy for you. Bye for now. Take care. Remember to be kind, make healthier choices, and keep learning. Keep watching isaykids. Subscribe now. We are coming back with more very, very shortly. Have a lovely day. Bye bye.